The arrival time, burst time, and priorities of five processes are given as here. Five processes P, Q, R, S, and T with their arrival time, burst time, and priorities are given. The question is, for the priority scheduling algorithm, determine the average response time. Ignore the context switching overhead. Here, the priorities for scheduling this process, we are using priority scheduling algorithm, and one is given as highest priority. So let us write Gantt chart for this algorithm, for this schedule. Here all the process arrived at time 0. So the CPU is as we are using priority scheduling algorithm, the process with highest priority is allowed to take the processor first. So processor priority of process S is highest 1. So CPU is assigned to process S at time 0 to and the burst time of this process S is 8. So in between 0 and 8, 0 to 8, process S is executed, and after 8, at the time 8, when process S is completed, the next process with the highest priority is R, whose priority is 2 and its burst time is 6. So from 8 to 14, process R is executed. Once R is executed, the process with highest priority is P, whose priority is 3 and its burst time is 2. So in between from 4 to 16, process P is executed. After P, T is having highest priority, which is of 4, and its burst time is 10. So from 16 to 26, process T is executed, and from and the last process is Q, which is of priority 5, and its burst time is 4. So from 26 to 30, process Q is executed. So this is the Gantt chart. Here we have to find the average response time. Average response time. So what is response time? Response time is the time taken by the process to start responding. Response time is the time taken by the process to start responding, but it is not the time the process takes to output the response. So response time of process S is it is arrived at time 0, and so the response time is nothing but the time interval time taken to give the first response. So here response time of S is 0 and response time of R is 8. Response time is of P is 14 plus T is 16 and plus Q is 26 by total number of processes. Total there are 5 processes. So if we simplify this, we'd be getting 12.8 minutes, which is option A.
The system uses the demand paging for its implementation. The probability of getting page faults is 0.25. The normal memory access time is 200 nanoseconds. If it takes 2 milliseconds to service a page fault, then what is effective memory access time? So in a demand paging system, the effective memory access time, there is one formula, that is 1 minus p into memory access time plus p into page fault service time. So p is the probability of getting a page fault. Already we know that 0.25 is the probability of getting page fault. Then 1 minus 0.25 become 0.75. So 0.75 into memory access time is 200 plus p is 0.25. 200 nanoseconds is the memory access time. We have to convert 2 milliseconds into nanoseconds. So 10 power 6 nanoseconds is 1 millisecond. So 0.25 into that is 2 followed by 6 zeros nanoseconds. So this value is equal to 500,150 nanoseconds. So that is option C is the right option. English, list A is access matrix, aging, LRU and paging. List B is additional reference bits, fragmentation, priority and protection. Access matrix is which is the implementation of protection system. That means using access matrix we will have some domains and objects, and access rights will be implemented there. So it is related to protection. Aging is the technique of removing starvation, where the starvation is a problem in priority scheduling. So aging is a technique we use for gradually increasing the priorities of process. So Q is related to 3. P4, Q3, and LRU, least recent used algorithm, can be implemented using additional reference bits algorithm R1. And paging, so it is related to internal fragmentation, because paging is suffering from one fragmentation that is called internal fragmentation. So it related to fragmentation. P4, Q3, and R1 and S2. So option B is the right option here.